Okay. Let me start. By the way, were there any questions from what we did yesterday before I begin? Or yeah.
Would the cost of having interface
Correct. Yeah. Right. So, okay. So that's a good question. So that's actually part of what I was going to get into in the moment. So imagine we sort of go back to this Landau theory, and we can sort of generalize it in a fairly straightforward way. But the point that we did yesterday was we said, oh, well, I can divide my system up into little blocks, and and crudely, let's assume that these are not connected. We said I can define, in this case, I was thinking of a scalar magnetization. So it only had like one direction in which the magnetic moments could point, let's say along the plus or minus z direction, right? And then we came from here and we said by evaluating the free energy of these little blocks, we can try and arrive at an expression for the partition function, which was written as a path integral over this scalar magnetization with weights that look a little bit like a Boltzmann weight. So if you wish, you can think of that as a beta times an effective Hamiltonian. And on symmetry grounds, we wrote that S of M of R was some constant part, which did not depend on the magnetization, but it could depend on other things. For example, phonons, if there is other stuff, all of that could appear in this S naught, right? And then we said, oh, there is a part that depends on the magnetization, which we can Taylor expand in powers of the magnetization itself, assuming it's small, and because it's evaluated on blocks, it's a nice analytic function. And so then we wrote down some, and at that point, I was just using some ABCs to write down the magnetization. So we had something with AM square of R, BM4 of R, so on, right? And then we said we are also allowed gradient terms. So the gradient terms that we wrote down, assuming that now these blocks are coupled, there'll be some energy cost to twisting the magnetization or to, making the magnetization deviate from its uniform value. And so we said, oh, there is some energy cost to bending the order parameter that looks like this, right? So here, okay. So with this, okay, that's one. The second thing we said is that these coefficients here, because they come from computing a free energy, it's not really just a Hamiltonian of some, of some given spin model. These coefficients will actually depend on temperature. So this will be some temperature dependent prefactor because it's coming from computing some free energy in these blocks. Similarly, B will be some function of temperature and so on. So all these coupling constants are in general functions of temperature, and they will contain all the detailed information about the solid is kind of buried in here in some way. Yeah. So now you can say, well, I can try and do this, and we'll do sort of calculations with Landau theory in just a second, but let's kind of answer the question that was just asked, namely what happens if I look at not a scalar order parameter, but imagine it's a vector or it's something else, right? And so you can kind of say that, okay, I can do the same thing where instead of these blocks having a scalar magnetization, they have a net magnetization that points in some direction in spin space, right? So there would be some vector magnetization that I should be working with. And now I can write down my action as a function of this, functional of this vector magnetization. Okay. Again, I have to integrate over all those vector magnetization configurations. But if I write down this action, then say, oh, well, there is again something that's some constant, right? There would be again integral over all space. And now I can write down objects of this sort, but now I should remember that not only do I have to have, time reversal symmetry, which is what we used here to write down that m going to minus m. So odd terms in m were not allowed here, except for the one which involved a magnetic field which explicitly breaks time reversal symmetry, right? So now we have to ask, not only do I have time reversal symmetry, I also want to impose some other symmetries in the problem. For instance, I could impose spin rotational symmetry in this example, right? And so if you do that, you say that, okay, well, then the kind of terms I can write down would be some coefficient, but now m square has to be replaced by a quadratic function, but it has to be also invariant under spin rotations or rotations of the magnetization. So the only thing that you can write down is a dot product of the magnetization with itself, right? So that's the analog of m square, right? You can write down similarly fourth order terms, right? And the fourth order term, that the simplest fourth order term that we will write down is just m dot m whole square and so on, right? So this will be like m to the fourth. So that's rotationally invariant. But now when we come to gradient terms, similarly, sorry, let's write down the magnetization. Well, now we'll say, oh, there is a term that must be proportional to now a vector magnetic field that is dot producted with this vector magnetization. Okay. But now the question was, what do I do with these kind of gradient terms? Okay. And the simplest kind of thing that you could do is if you demand independent rotations in spin and space, which is typically what happens if you don't have atomic like spin orbit interaction. So imagine I think of like a non-relativistic problem where spin and space are basically decoupled from one another. Okay, then I should really think of a term that is rotationally invariant in both spin and in space separately. Okay, and so now I can write down kind of analog of the stiffness here would be some stiffness term, but now I'm going to use the Einstein summation convention. So let's write it as a derivative of the ith component of mj di mj, and I'm summing over. So here I goes from 1 to the number of dimensions. J runs from 1 to the number of components of the spin, in this case, three-dimensional. Let's say it's a three-dimensional vector, right? So I goes from 1 to space dimension d. J here, maybe I should have used a different. Let me use, I don't use, actually, let me not use alpha, beta, and so on, because we'll use that for critical exponents. So let me just call it J, but I and J run over different things here, right? So I runs over space dimension, J runs over 1 to, let me call it the spin dimension, B spin or something, right? Number of spin components. Let me call it N, number of spin components. Okay. So the usual Heisenberg model, which is if I have a three-dimensional, spin vector, would be that this runs from 1 to 3, n goes from 1 to, and n is 3 in that case, and space dimension could be whatever 2 or 3 dimensions. Right? And so that would be the analog if you have separate spin and space rotations. Okay. But this need not be. So this is, what you'll think of as a Heisenberg magnet. Let me call it no spin orbit coupling here. I'm just shortening it to SOC to say that I have these two independent symmetries in the problem. But you could also write down, models where, in fact, that's not true in solids in general, right? In general, solids, I mean, there is spin orbit coupling, right? And so space and spin rotations, you can't treat them independently, okay? And so in fact, the spin degree of freedom will only have in some sense as much symmetry as your crystal itself, right? So if you have a cubic crystal, I cannot have full spin rotational symmetry, unlike here or here, sorry, unlike here or there. I will only have discrete rotational symmetries associated with the crystal, right? And if you do that, in fact, you're allowed more terms at this level. At this level, you're not allowed more terms because, for here, the action for, let's say it's still a vector magnetization, right? But let's imagine it's a cubic crystal now, where I only have the symmetries of a cubic system. Then again, I'll have S naught plus this integral. This one, let me write it component-wise, mx square plus my square plus mz square, right? And if I do that, then you say, oh, that is also invariant under the symmetries of a cube, which takes x to y to z, right? So in fact, this is invariant under the symmetries of the cube. And so in fact, this will not change. And let me just write it as loosely as am square, but you know that it's this m dot n, what I mean. Okay. Let me write it like this. Okay. This one certainly goes through. Obviously, if it has the full symmetry of any rotation, it obviously has the symmetries of the cubic system. So I will of course have terms which are this, right? But in fact, if I have lower symmetry, I'm allowed more terms in the Landau theory, right? Because terms which are invariant under this may not necessarily be invariant under this higher symmetry group, right? So in fact, you're allowed terms where I could write down some other coefficient times, mx4 plus my4 plus mz to the fourth power, which is not invariant under rotations of the vector m, but it's invariant under the rotations, the discrete rotations associated with the cubic crystal. Yeah. Similarly here, right? Once I allow for the locking of spin and space, I don't necessarily have to write down terms of this sort. I could write down gradients. It turns out at lowest order, it's not allowed. But at higher order, I can certainly write down gradient terms. And I'm not going to write it out explicitly here, but you can certainly write down gradient terms which are not invariant necessarily over spin and space separately. Right. So one term of the sort which may or may not be allowed is of the sort that he was just mentioning, which is I could write down, can I write down a term which is like the divergence of the magnetization whole square? And there might be other terms that one can kind of think of and try and write down other sorts of terms here. So and in each case, one would have to check whether those terms are invariant under the rotations that correspond to the crystal environment in which you expect this magnet to live. Yeah, is that fine? Yeah, okay. Okay, let's do one more example because that will serve to kind of illustrate, one of the points that we made yesterday about sort of this idea of universality, right? And you'd say, okay, I can kind of do all this. And part of the universality that we'll see comes from the fact that, okay, at some level, I have not told you about the microscopic information that went into these, but that's a bit of cheating because if I wanted to derive this from some microscopic Hamiltonian, in fact, A, B, C, and so on, all these coefficients will in fact contain all the information that's there in the Hamiltonian. Right? And there are higher powers here. So there's an infinite amount of information in here, which can in principle incorporate as complicated a Hamiltonian that you might wish to start with at the microscopic level. Yeah. But anyway, this will be part of the universality will stem from the fact that many of these terms actually will not matter at the phase transition. And that's where some sense of universality will come from the fact that although there's an infinite number of coefficients here, and in principle, I can encode a ton of information, not all of that information will be important at the critical point. Okay, and we'll see that more clearly in a bit. Okay. But the other example I wanted to do was imagine I took not a magnetic system, but let's take a system which corresponded to the Bose condensate. Okay, and for a Bose condensate, remember that we said, oh, well, I should be looking at the momentum distribution going from, being 0 to non-zero, n of k equal to 0 as a function of temperature, right? But we said, in fact, there's a more fundamental order parameter. This is not the correct order parameter to look at. The correct local quantity to look at was, some object of this sort, right, which corresponded to the expectation value of this annihilation or creation operator in this particular instance, right? And so we said, oh, this is in fact my order parameter. So there is some complex number now because this is not Hermitian. The expectation value need not be a real number, right? Or equivalently, if I wanted to write down the annihilation operator A of R, sorry, these A's are different from these coefficients A's that I'm using here, right? So these annihilation operator for the boson. So this would of course be the complex conjugates of each other. So this is going to be phi of. Okay. And now you say, well, I want to write down now my theory such that I want to write down exactly the same way. I'm going to start coarse graining, do these block construction and write down the action. Okay. And you'd say, well, now my action is functional of this complex number. So I have to define the complex number everywhere. I'll give you what this action is. And same way, there's going to be some part. And I'm going to start throwing away this in a second, but just keep it in mind that there are these pieces which come from other stuff. And then there's a part that depends on the order parameter. Okay. And now you can ask, well, what am I allowed to write down as terms in my free energy of this action on my free energy function, a Landau function? Okay. And I have to say, well, I have to rely on symmetries. Okay. And one symmetry that is true for, if I have some microscopic model of bosons, it will have in general some kinetic energy. Let me just call it some hopping of particles. Let's say on a lattice, let me call it I and J, right? So it will involve something like a hopping of bosons between. I'm assuming everyone is familiar with second quantization. Just while writing this down, we won't really need to use it for much of the course. Okay. But this just involves sort of bosons hopping between neighboring sites on some lattice. And sorry, I have to sum over Ij. And I'll have some interaction. So let me just write down some simplest interaction as some Ni square, let's say. Okay. So if I have two bosons at a site, it just costs some energy U. So there's some theory of interacting bosons. And one symmetry that's there in this Hamiltonian is that if I take AI and send it to AI times e to the I theta, so I take all the boson operators and rotate the phase of these bosons by some amount, then of course this Hamiltonian is invariant. Okay, this angle doesn't depend on the site. It's a global phase rotation, right? And just like in quantum mechanics, I kind of don't care about the global phase choice in some sense, in the crude sense. Here, in the Hamiltonian, it just means that if I do this rotation, it cancels out everywhere. Theta doesn't appear anywhere. And I could as well use this transformed, if I want to call this some new boson operator, it will, the Hamiltonian will look the same when written in terms of these new boson operators. Right? So that tells us that we have some U1 symmetry. Okay, and it is global because theta is not a function of position. There's a global U1 symmetry in the problem. Okay, and that must be encoded in the action that we're going to write down, right? And so this means I'm not allowed to write down terms of the sort, well, I have, I'm going to keep calling it A, even though maybe I should have called that something else. Yeah. But this A is just some coefficient. I'm not allowed to write down terms of this sort. This is not allowed in the problem at all, right? Because if I do a rotation, then this is going to change phase. And so this action would not be invariant, but it's really like a free energy should we have the same symmetries as the Hamiltonian, right? And so the lowest order term I could write down is something like phi star phi. And now I can start writing down similarly. Again, I don't have any terms that are cubic. I can write down something like phi star phi whole square and so on. Right? And when it comes to the stiffness, right, then I want to write down gradient terms. Remember that this is it's a scalar, it's a complex scalar field, right? So I can write down a term that is like grad phi dot grad. Let me write it as phi star grad. You can think of it as grad phi mod square. Okay. So these are the kinds of terms that you can sort of imagine writing down in this particular case. Okay. And now you see that we can do a little bit of trickery here to rewrite this in a form that's slightly different, where imagine instead of writing this complex number as it is, let me try and write this complex number in terms of its real and imaginary components, right? So let me call this some phi x plus I times phi y. Okay. Then we'll say, oh, that means my action here is now I have to specify both the real and the imaginary part. So both these are two real fields, but they correspond to the real and imaginary parts of this complex phi, right? This will have some S naught plus, and now I can start, decomposing this in terms of real imaginary parts. And from here, you see that, okay, one term that I'll get from here obviously is A times, phi x square plus phi y square plus B times, phi x square plus phi y square whole square. Right? That's this term. Right? And you can write out, other terms. And finally, there is a piece coming from this gradient. And now this, you will really see that, okay, I have terms which is like grad phi x, right? But I'll also have grad phi y, and there are no cross terms. So you're going to get something like grad. So you'll get terms that look like because there's a complex conjugate, the cross terms basically cancel. Right? They will have i's in them, and of course you can't have i's sitting around in a free energy. So you'll get terms that look like this. Okay. But now you see that this particular action that we have written down, okay, is exactly the same as this action here. Okay, provided I identify this M with a two-component magnetization vector. Let's say M is only mx and my, but no mz, right? Then this looks like mx square plus my square, but I can't really tell the difference between that and this. It's just a relabeling. I'm calling M as phi here, right? Same way the m to the 4 will look like this term and so on, right? And so you see from here that this means that as far, even though the microscopic description of these two problems is very different, one is a magnet with having two components of its spin, one is some Bose condensate, right? Really at the level of Landau theory, if we think about it in terms of symmetry, they'll have the identical action or the identical free energy, right? So the S for what people call the XY model, which is a model of magnetization. It's XY because it only has X and Y components of magnetization, right? Is exactly the same as the action for this BEC. Let me call it BEC. Okay, but you know what I'm referring to this entire thing, right? And so you see that, so this is now you begin to see that, oh, there can be sort of a different sense in which I can talk about universality. One is maybe different magnets which are microscopically different might end up having the same looking action of this form, even though the coefficients in detail might differ, right? But it's also possible that two systems which are completely different physically might also end up having an action that looks exactly the same. I just have to relabel, I just have to physically kind of differentiate the meaning of the order parameter. But other than that, the action looks the same, mathematically the same. Yeah? Okay. I'm going to erase something here. By the way, some student had, I think, who was attending online had asked me about sort of textbooks or resources. So there are, I mean, if people are kind of, beginning grad students or undergrads, so there's a book by Nigel Goldenfeld that talks about the renormalization group, which is a very good one. There's also a book by Meren Kadar, so he has like a 2-volume book, and the second one kind of talks about phase transition. So either of those would be good resources. I'll also ask if, I mean, I have some notes, but these are, probably not very useful scribbles, but I'll ask if I can post them. Maybe I'll post them. Yeah. Okay. So what? Okay. Any questions at this point? Or, yeah. Right. So the assumption that we are working with is that, when we talk about phi as, okay, so the reason, okay, you could have asked the same question here, right? Mod of M, where M is some vector. The reason is that when we are computing the free energy of the system on little blocks, we expect that whatever corrections you're going to get are nice analytic, corrections. So I can do like a nice simple Taylor expansion, right, in this vector or scalar order parameter, right? And so mod M is not allowed in such an analytic expansion. In this case, yeah, I'm assuming that I've coarse grained a little bit, right? So I was using the lattice coordinates as ij for AI dagger aj. But if I want to think of some coarse grained field, then I should think of, take my, imagine I could give. So when people do mean field theory of this at the lattice level, you would actually give expectation value to AI on the lattice, right? So I'm imagining that I can define that, but now coarse grain that complex number over some region, over some small region, right? And exactly in the same spirit as here. The magnetization was in a lattice model is the expectation value of the spin at a given site. And then I'll do that and then coarse grain it to get my M. Okay. Any other questions? Okay. Okay. So let's then kind of move on to asking, well, why is this useful? I mean, beyond the fact that I see some hint of possible universality, right? But I don't actually see a phase transition yet in this problem, right? And one of the insights of Landau was that even though my action itself, and let's go back to now the simple one with just a scalar, but more or less everything I say here will apply to the more complex ones. So his point was, okay, I mean, we have the separation between the part coming from everything else and a part of the action that, comes from terms that depend on the magnetization. So everything here is a function of R, a vector position. So Landau's point was twofold. One is that you say, well, I don't really care about this constant piece if what I'm looking at is close to the position of where the phase transition is going to happen, right? Because of course you could have something where the spins and phonons talk to each other. So that will be some complicated thing here, where I have some coupling between spins and phonons. So all of that, are terms in principle that are allowed that are beyond, what we have written down. Here we've kind of nicely separated it out onto stuff that is background and stuff that depends on magnetization, right? More generally, of course, the magnetization can couple to other degrees of freedom, okay? But in the end, I'm assuming that the only important thing that's changing when you go through this transition is the magnetization itself. And all the interactions, etc., are not really singular. So the interaction, the magnetization with other stuff is not changing suddenly at the critical point, right? And so if that's the case, then, these coefficients are functions of temperature. And that's an assumption which, one must question if one is looking at quantum phase transitions involving, like, imagine I have fermions, some gapless fermions coupled to, magnetic moments and so on. These are assumptions that one has to question, but we'll come back to that towards the end of the course. Okay. So here you would say, well, these are then coefficients that are functions of temperature. And this one here is just the rest of the stuff that I don't care about. The assumption is that this is smooth, but somehow, this stuff is what he would call, singular, not in the sense that it's divergent again, but in the sense that it's not going to be a smooth function as you change temperature. Okay, not the coefficients here, but the free energy once you calculate it will acquire corrections which are not simple analytic functions of temperature. Okay. So this, let us drop this, okay, and let us focus on just this term. And people often kind of, refer to this piece then as, things coming from kind of singular parts of the free energy functional or this action, things that depend on the order parameter. There's all this stuff which can be smooth and nice and regular as you tune temperature, and we'll just throw them away from it. Okay. So that's one. The second is the idea that, okay, look, to begin with, let's assume that the magnetization is more or less uniform like in mean field theory. So I can even forget about terms involving the gradient of the magnetization. Let's say it's flat, the gradient is 0. Okay. And if you do that, then the singular part of this free energy, and let me drop this subscript for now because we're going to write it many, many times. So let me just call it S. This S, instead of being a functional of M, if M is independent of position, it's just a function of the magnetization. Right? So this really becomes like S, which is a function of the magnetization. You give me a magnetization, I'll give you you give me one number as input, I'll give you one number as output. Here, you gave me an entire function as input, and I give you one number as output. Yeah. So S of M then is going to be just a volume, because this is all independent of R. It's going to be a factor involving the volume times this stuff here, right? So it's going to be A. And so here, let me actually put back the R dependence here. Now it's really independent of R. So I'm going to get something like A M squared plus B M4 plus higher order terms. And what Landau realized was, if I am going through a transition where M goes from being 0 to being some small non-zero value, then clearly the higher order expansion terms are unimportant. And we'll make that more precise in a very definite way later on, right? But it's going to be unimportant. So really, I should be looking at simply a term which involves quadratic and quartic terms in my expansion. Okay. And if that's the case, you see that what I should do is I want to minimize this free energy of this action with respect to the value of this magnetization. Okay. But you see that that answer can depend very strongly on these coefficients, right? So two things. One, you say as well, imagine I plot what this function looks like, for different A and B, right? So if A and B are both positive, I'll get something that looks like this, right? And the minimum is at 0. Okay. If A is positive, B is negative, then I'll get a function that, basically is going to be, in general, it will look something like that, right? So at small values of M, it looks like you'll get something that has, sorry, I don't mean for this y-axis to be 0 here, right? But you'll get something that at small m has positive curvature because A is positive. But at large values of magnetization, if B is negative, then this is going to, and it's going to become large. So this is the case where A is positive, B is negative. Right? And I could take the case where, of course, if A is negative, B is negative, this entire thing flips, right? But if A is negative, B is positive, then I get something that looks like. That's the shape of these curves, okay? And from here, you can say, well, this means that the minimum here is at 0, right? So if I minimize this function, I'll get the equilibrium value of the magnetization. So let me just call that M naught as 0, or you could call it M equilibrium, but the magnetization is 0. Here, this is not a good thing Why is this not a good thing? M is not bounded, right? So I can just keep on decreasing my free energy by going to larger and larger, and so this is kind of unphysical. So this will kind of, in this particular case, okay, there will be other examples, and maybe I can have like some problem sets if people are interested in where, you would actually be interested in the case where B is less than 0. But you would have to then put in terms which are, let's say, 6th power that will eventually turn it and go on. And finally, look at this case, and you see, oh, in this case, in fact, I do have sort of equilibrium magnetization, which can take on 2 possible values which are non-zero, and it's stable once you sit there, then it's stable, right? And so you realize that, okay, by playing around with these coefficients, you can actually try and describe a system which in equilibrium has no magnetization. But if I allow this quantity A, this coefficient, to change sign, and remember, these are functions of temperature from the coarse graining, then in fact, you can describe a state which is magnetization that is non-zero, but it can take on these 2 values, right? The free energy, as written, is still invariant under m to minus m. So it's even function of the magnetization, okay? And so clearly you can ask, well, this doesn't really correspond necessarily to a state with non-zero magnetization in equilibrium if my system can thermally, fluctuate from here to there, right? So remember, in equilibrium stat mech, I'm not talking about dynamics. I'm just asking about, I'm going to access all possible states which all have the same energy or the same free energy. Everything is allowed, right? So in principle, if these 2 have the same free energy, then they should appear with equal probability in my, when I'm sampling the system. And so in fact, the net magnetization would then be 0. Okay. But the point is, then it becomes a question of dynamics, which is that if I try and start here, how long would it take for me to end up there? Okay. And the only way you can do this is you have to create some defects. You have to take some region with uniform M, flip some droplets, and eventually kind of flip enough of them that your entire magnetization overturns, right? But this barrier here is going to scale with the system size. Remember that this, in some sense, was the total free energy, which scales with the volume of the system. And so this barrier, whatever it is also going to scale with the volume of the system. So as you make your system larger and larger, this barrier to going between these 2 states is going to get larger and eventually diverge in the thermodynamic limit. Okay. So in a large enough system, you will not on lap time scales be able to go from here to there, or in a system size going to infinity limit, you will truly never be able to do this no matter how long you wait. Okay. So then this tells us that I can actually describe a phase transition now by saying that all I need to do is say that as a function of temperature, this coefficient A is going to be a function of temperature. Okay. And for simplicity, we'll, just rewrite this up to coefficients, because I can always scale things to absorb. I can rescale A and absorb factors into magnetization if I wish. I'll kind of rescale this and say that, well, maybe what A does is look like this reduced temperature that we were discussing yesterday in mean field theory. Namely, A is going to be at least proportional to, but I'm just going to set it to be equal to. Okay, it doesn't really matter because I can absorb these coefficients. It's going to be the distance to this critical point normalized suitably, such that if T is bigger than TC, then I'm going to realize this scenario on the left. And if T is less than TC, I'm going to realize this scenario on the right. And B here is just going to be some number which is not negative, it's positive, but for simplicity, I don't have to worry about its temperature dependence. Yeah. So B of T we'll assume is temperature independent. Okay. And so let's call this the reduced temperature little t that we were using yesterday. Okay. And in fact, yeah. And this B of T, at least in textbooks, most people kind of use a convention to, this is just a renaming of, and I was calling it ABC, but people call the coefficient very often as labeled U. So if you see it in textbooks, that will be a different notation. But we'll assume that it's some temperature independent constant. And so now we see that what this Landau theory now is going to be that this S of M, the singular part, let me divide it by the volume. So I'm not going to talk about the factor of volume. We'll talk about free energy densities and so on. Is going to be then written as T times M square plus, sorry, maybe I'm sorry, I think in the notes, I think even in the books, I think there's some conventional factor of 1/2. So there's some T by 2 plus U times M4. This is the way it would be written in, although people use different conventions in different books for denoting this. Yeah. Other odd power of T. Yeah. So you could have T cube, but it'll be small, right? So T cube will be smaller than T. So if you want a function that changes sign, it just goes through TC. Then from mean field theory, we know that things depend in this form, right? And if you wanted to write down corrections which are like T cubed, it will be much smaller than. Correct. So right. So we are making an assumption that's right. So what we are making an assumption is that I have already Taylor expanded my free energy functional in powers of the order parameter, okay, with coefficients that depend on temperature. And now if I'm sitting close to the transition temperature, we are doing a further Taylor expansion of these coefficients in powers of distance from the transition. Okay, so if you're close to the transition, that's another expansion parameter if you wish, as I just pointed out, right? And you can again ask, is that always valid? Does it break down in some case? And so these are questions that one has to ask, but for now, we'll kind of go with this. Yeah, all right. So with this, one can now, of course, let's say I add in a magnetic field, then this would be some H times M. Okay, and with this, we can try and ask, well, can I recover some things that we did in mean field theory from this Landau theory, right? And so you'd say, okay, I can try and compute let's say the equilibrium magnetization at 0 field, right? So imagine H goes to 0 and I want to compute the equilibrium magnetization. So you'd say, well, what I really should do is take ds dm, set it to 0. And of course, I have to find the one that corresponds to the minimum. We know that there are 2 places where the derivative vanishes. There's a third one where the derivative also vanishes, but it's a higher energy or higher free energy point. So I'm not going to look at that, right? So exactly like in the mean field theory, there are 3 roots to that problem, to this equation, right? Only 2 of which are low free energy, 1 of which is a high free energy. So this here is going to give us an equation that's Tm plus 4 times U M cubed is 0. Let me call that M naught, because now that's the equilibrium value, okay? And from here, you can read off that, M naught is then the square root of negative T divided by 4U. This is when T is less than 0. When T is bigger than 0, of course, the answer is just 0. Okay. When T is less than 0, there are these 2 non-trivial roots. So it's plus or minus. Or maybe I called it M naught and minus M naught. So let's just say M naught is this. And the magnetization can be plus or minus M. Okay. And you see that this has precisely the same dependence on temperature that we found in mean field theory. Namely, this thing goes like the magnitude of the reduced temperature for T less than 0, of course, right? To the power 1. So in mean field theory, we got an equation that kind of looked very similar, except this came from expanding the tan hyperbolic. Here, there is no tan hyperbolic. We're just writing down this is the only term. So you can calculate other things. Like, for example, you might say, well, I want to calculate the susceptibility, right? So to get the susceptibility, remember, I had to keep a small non-zero field and then calculate the resulting magnetization. And let's do it in this phase here where I'm in the phase where the symmetry is not broken. So I'm in the phase with where there is no magnetization in the problem. Then you'd say, well, then the only way I can have magnetization is because I stick in a field, I'm going to induce a magnetization. And now you say, let me try and again do this minimization, but keeping H here, then you'll say that, okay, I have T m naught plus u by 4 m naught cube minus H is 0. Right? And now you realize that, okay, imagine the magnetic field is what is producing the magnetization. And we expect that, oh, well, H is small. M naught is of order H, you would expect, if things are linear. Right? But if that's the case, then M naught cube is going to be extremely small compared to H and M naught. Right? So in the limit of M naught, H small, and T being positive, right? We can drop this middle term here. And so we end up with M naught simply being equal to H divided by T. Okay. And this means my susceptibility, and this is T greater than 0. So this means my susceptibility for T bigger than 0 scales like 1 over T, which again was something we found from the mean field theory. So we see that, okay, we can kind of recover various things that we calculated from a microscopic lattice model mean field theory by doing this coarse graining, making certain assumptions about the structure of this action or this free energy functional, minimizing that to get the equilibrium magnetization susceptibility and so on. Okay, so this looks like a promising way to kind of then say, well, this is a much simpler problem than picking a specific lattice, picking a specific. This thing is to say, well, I'm just going to write down Landau theory and do this extremization because, of course, I get all the same answers. Not quantitative, but qualitative behavior, right? So let's go one step further. I didn't do this, but you can also do this in the lattice version, but I did not do it. But you can say, well, what if I don't do this assumption that the magnetization is uniform? Right? By the way, up to this point, are there any questions? Or yeah. So let's assume that we want to go one step beyond this Landau theory. Then say, well, I really want to keep terms where the magnetization is not constant and ask, well, what does that do? Okay. Because you see from here that there was a certain logic to ignoring terms higher here, like M6, M8, and so on, by saying that, oh, look, M was small, and I can drop those terms. Right? Here you might say, well, this is M square, order of M square, so maybe it's not a good idea to drop it. Let me keep it, and let's see what happens. Okay. And certainly, one of the questions we will want to ask is, are those spatial variations actually important in kind of changing the behavior of this? Okay. I'm going to erase this. Sorry, just a quick note. So this picture here where we went from here to this, of course, is a simplest example of symmetry breaking where even though my free energy looks like it's invariant under M to minus M, my solutions will pick one of the two sides. And that's the spontaneous breaking of the symmetry that's present in the problem. Okay, so let's say I sit here, and then I find I can't actually go over to the left, then I'm stuck there forever, and that's the broken symmetry. Okay, so time reversal symmetry in this instance is spontaneously broken. Not here. This is T bigger than 0, and then this. And you could, of course, pick either one of them with just as likely. Okay. All right. So let's ask what happens if, or when might we be interested in keeping the terms that involve not just a constant magnetization, but let's go back to the case where the magnetization is in general non-uniform. And again, I'm only writing down now the what we call the singular parts. Right? So you'll have some 1/2 T m square. These are now functions of position. M square and so on, but I'm ignoring all the higher order terms. And now let's ask, well, can I try and look for, examples where what if the magnetization was not uniform, and I'm trying to look for solutions which minimize this free energy, but in this non-uniform case, okay? So then what you have to do is you would have to say, well, the equivalent of taking a function and minimizing with respect to the number is to say, well, I'm going to take this functional and minimize it with respect to all possible functions that I could have come up with. So this is taking a functional derivative. So this is saying, well, that I'm going to take this action, right? You give me some m of r that I'm going to stick in here. I can put in many functions, right? And now I want to try and extremize by kind of take this action and take its functional derivative. So have people seen functional derivatives before, or has anyone not seen functional derivatives? Okay, so it's a little bit like how you do, ordinary derivatives. You would say take m and send m to m plus delta m if I wanted to do an ordinary derivative, and then take the limit where I take the difference between, having m and having m plus delta m, and then dividing by delta m. That's what you do for a normal derivative. Here you take m, this function m, modified by some delta m of r. So it's a function that, it's a small change in the function, right? Then expand this out to linear order in delta m. And the coefficient of delta m within the integral essentially is what this functional derivative is. Yeah. But if people have not seen it and maybe people are not speaking up, just go and maybe it's a good idea to maybe these books, some of these books will have a discussion. Okay. So for this part, more or less you can treat it as taking derivatives here for the purpose of most of these terms. So this is going to give me something that is proportional to t times m of r. This one here is going to give me some 4 times u times m cube of r minus h. And now this one here, we can do an integration by parts to get it in the form where it is minus kappa by 2 times m times del square m. And so the functional derivative that you get from here is just minus kappa times del square m. So if you've not done it, you should work it out. But that's the answer when you take the functional derivative, and we want to set this to be 0. In general, this field need not be a constant. So let me call it h of r m. And here all m's are functions of r here. So this is also going to be some h of r when you take the function. So one place you see immediately where this kind of thing will be important, right, would be to say, well, imagine this h was not a constant, then certainly I have to worry about non-uniform solutions to this problem, right? Setting m equal to a constant will kind of kill this term, right? And this will have some very specific number if m was a constant, but if that's a function of position, I will not satisfy this equation. So I have to have m to be a function of position, okay? And if m is small, then we can try and say, well, let me do what we did for the susceptibility calculation there, which is let's assume that t is bigger than 0 just for simplicity to work this out. Then say, well, I can omit m cube because there's no magnetization to begin with. Anything that's induced is small. I can drop this term. Okay. And then I'll be left with an equation that is linear in m. So I'll get kappa del square m. This is some t. So let me write it as plus mod t here. Oh, sorry. No, this is in the, sorry, this is fine. This is in the case where it was t was bigger than 0. is equal to h of r. Sorry. Is this fine? Yeah. So I'll get an equation that looks like this. Okay. But you see that it's a linear equation in M. And there is nothing funny about the coefficients here. The only thing that depends on R is out here in front. Okay. And so of course, a very simple way to solve this is to say, well, I can go to Fourier space and solve this. So I can do this by Fourier transforming M and rewriting, going from M of R to its Fourier transform M of Q. And I'm going to use the same M here instead of some twiddle or something. Just from the argument, we'll know that that's the Fourier version. Okay. So here we can try and solve this by saying, well, what are you going to get if you insert this Fourier decomposition? You're going to get that, I'm going to get kappa times Q square, because this two derivatives will bring down two factors of Q times M of Q plus, T times M of Q is going to give me the Fourier transform of this field here. So these are all vectors. Right. And now you can very easily solve this problem because it's algebraic, right? And so this one is going to give me M of Q, which is HQ divided by kappa Q square plus T. And now to get the magnetization profile in real space, we just have to inverse Fourier transform back to get the answer as a function of position. Yeah. Okay. So that's the answer in Fourier space. And now all we have to do is do the Fourier transform. But let's do the Fourier transform in a simple case where let's assume that h of r is non-zero just at one point in space. So let's say the origin, and I say that h of r is non-zero just at that one point. So it's like a delta function. Okay. Let's replace it by a delta function, which means that in momentum space, h of q is just going to be a constant independent of momentum. And I'm being sloppy here about factors of volume and so on. So I'm not doing this, carefully enough, but this is, the fact that it's a delta function, it's highly localized in real space, is going to be completely flat in momentum space, which means M of Q in this case is going to be a constant divided by, this T plus kappa Q square. Okay. And now if I want to get M of R, I have to Fourier transform this function here. And this function, is, it's Fourier transform. You can kind of do this. Let's say the most easiest is in 3 dimensions, but you can also do it in 1D, 2D, and so on. So M of R is going to be obtained by taking this, and let's say we do it in 3D. And I'm not going to do this integral now, but I'll write out the answer. Okay. And you can do it by, you have to do the angular part of this integral, and then you have to do the radial part of this Q integral. And the radial part is the only one that appears here, right? So all the angular parts you can do easily, okay? And the radial part, what you're going to get is something that depends on, T plus KQ square in the denominator. And this one you can do using, different ways, but, maybe the simplest is to do some kind of contour integration to get it. But this answer here is that this is going to go proportional to 1 over square root of the distance. This is the magnitude of R. I have picked the origin to be the point where the field is non-zero. With that definition, this R is the distance from that point. Okay. Times e to the minus R divided by a certain length scale, and this is going to be true at large distances, where this length scale psi, you can read off from recognizing that there is a special momentum here, which is the square root of t divided by k, gives you a momentum scale. So the inverse of that is a length scale. Right? So this is going to go like the square root of k divided by. Okay. We could have done this in the mean field theory by similarly trying to solve the mean field equations with a magnetic field that's non-zero just at one point. I didn't do that, but it gives exactly the same result, namely that there is a diverging length scale which goes like the distance to the transition point raised to the power minus a half. And this is going to diverge as you get closer and closer to the critical point. This length scale is going to diverge. Okay. And I kind of mentioned this yesterday, but we didn't work it out. But here is the case from Landau theory. Okay. And so what this tells you really is that when you're very far from the transition temperature at very high temperatures, then all the spins only have short distance correlations, right? So if I take the spin at one point, then the spin maybe on the neighboring site will want to point in the same way. But by the time you're at the third or fourth spin away, basically it has no knowledge of what is going on here, right? But when you come closer and closer to the transition, clearly this tendency to have spins wanting to point in the same direction will grow, because eventually when you break symmetry, they all point globally in the same direction, right? So there's a growing tendency for the spins to point in the same direction, and that's reflected in this growing length scale over which spins want to point in the same direction, right? Okay. All right. So what we see from here is that Landau theory gives us various things, okay, like thermodynamic properties and this idea of this growing length scale in the problem. Okay, and so what we want to do now is to ask, well, and all these results, by the way, as I mentioned, agree with everything that we did from mean field theory. Okay, so let's write out sort of what the, can I erase here? So let's basically summarize what we get from Landau theory for these different quantities. So remember that we had this definition of these various exponents yesterday, where we said various things diverge or become singular when you get to the vicinity of the phase transition. And we were asking, well, how do I characterize the singularity? They all look like some kind of power laws, okay? And the only thing that characterizes them is, what is the power in the, what's this exponent of this power that tells you how fast or how slow something grows or goes to zero or something, right? So we define various exponents. So remember that we had that the magnetization goes like mod t to the beta. And this is, of course, when t is less than zero. Okay. And we found that beta is 1/2. Okay. And this is mean field theory. We did it yesterday, but we also saw that this is true in Landau theory. The growth of the magnetization, right? We didn't work out the, okay, we worked out the susceptibility, and we worked it out at t bigger than 0, but it turns out it's very similar at t less than 0, except I have to remember to put a mod to make sure that I don't get some weird behavior. So it's t to the power of negative gamma. Okay. And let me not do this. And gamma was, sorry about that, gamma was 1. So it went like 1 over temperature in that expression. We wrote down what's the nonlinear magnetization at 0 temperature. And again, you can work it out in this Landau theory. You have a 1 factor of m times h, and you have some m cubed coming from um cubed. And if you do that trade-off, you get that this goes like h to the power of 1/3 at the critical point. And this defined for us that delta was 3. Remember, it went like h to the power of 1 over delta. That was our definition. So delta was 3. We have a new thing that we didn't do yesterday, but if you work it out in mean field theory, it also has a diverging length scale. And this one is that, again, we worked it out when t is bigger than 0, but there's a very similar result when t is less than 0. Namely, this goes like t to the minus 1/2. And here the definition is that this goes like t to the power of minus nu or mod t to the power of minus nu. So this exponent nu is a half. And so on. So there's more tables. So you can kind of work out what the specific heat is. And this goes like, mod t to the minus alpha. And in mean field theory, we didn't kind of work this out. But in mean field theory, the specific heat, behaves something like a, it's flat when temperature is above Tc, and then it kind of has a jump, and then eventually it does. Okay. So the specific heat, as a function of temperature, has a jump. And if we try and rewrite this in terms of exponents, it corresponds to an exponent alpha, which is equal to 0. Okay. So we see that, there is a whole bunch of these, critical exponents, and they all have some numbers which appear here, which you can kind of work out within Landau theory or mean field theory. Yeah. So you'd say, well, this looks all good, right? So there is some universality because, independent of the details of those coefficients, A, B, C, etc., these numbers don't depend on them at all, right? So it looks like all magnets should show exponents that are this, okay? And we saw it in two different ways, but really one can kind of get this answer more or less from dimensional analysis, okay? Where you say, well, let's try and, do this, and then we'll kind of ask why this is possibly. Actually, do people need a break, or do we just go on till 4? Any person raises their hand, we take a 5-minute break. I'm not raising my hand. So it's like I'm putting pressure. Okay. Nobody raised their hand. Okay, good. So let's do dimensional analysis. Okay, and this is going to be very crude dimensional analysis, right? So this is not some thing which will hold up to a real this thing, which is to say, well, I have some action, and remember that the partition function was written as some integral of e to the minus s. So this s here is basically dimensionless. Okay, and so then we said, what is this? This is some integral over space, but okay, let's do this. It's some integral over space, Tm square of r plus some u, sorry, m4 of r square minus hm. Right. And crudely, we can ask, well, I can ask what are the important terms that I want for any given quantity, and I want to try and match dimensions and try and see if it makes sense, right? So it's well, imagine I am interested in the magnetization. In the absence of a field, you would say, well, that went away. And let's assume that the magnetization is uniform, that goes away, right? And so really what I have to do is demand that I have two numbers here, and they have to have the same dimension. Okay, so you'd say, that means I could try and equate Tm square to um to the 4. They have to have the same dimension, right? And if that's the case, then I see that, m square must have dimensions of T over U, right? And that immediately tells me that m has dimensions that look like square root of T. Okay, and that's what this exponent is, right? Similarly, you can say, well, imagine I'm interested in the case where things are uniform, but I want to stick it in a magnetic field, right? They say, well, I'm going to ignore this higher order term. then I'm going to try and equate the dimensions of these two, right? So you would say, oh, Tm square must have the same dimensions as Hm, and that's more or less what we were doing when we were solving these equations, right? And you say, oh, that means M must go like H over T, right? And chi must be, gamma must be 1, right? And if you want nonlinear, you can kind of do this as well. And if you want length scales, you would say, well, I should compare Tm square should have the same dimension as this quantity here, but this we can rewrite it as some kappa times m squared divided by some length scale squared. The gradient is like some 1 over length. So that will be kind of the dimensional scaling. And so you'll say, well, m square cancels, but this length scale goes like 1 over square root t. Right? So you'll say all these results, in fact, should be extremely robust because, we did it in mean field theory. That's fine. You might say, well, it should depend on details of the lattice, model, blah, blah, right? But then we said, oh, we did it in Landau theory. And really at this point in Landau theory, even without solving any equations, we could have read off these things. Yeah. So then you say, okay, so this must be extremely robust. And in fact, this answer should always be correct. And then we find that there is an issue, right? So there are at least 3 different issues that we can highlight. Okay. One is you'd say, well, maybe I should compare it with experiments. Okay. Or these days one can do sort of very sophisticated numerical simulations. You can do Monte Carlo and study these kinds of spin models, calculate its properties as a function of temperature. So let me include kind of numerics there. And when I write down the numbers from these, I'm not actually going to say, which of these is used to get this, because we're only going to write down crude numbers for what one gets from experiments on numerics. Okay. So let's say we do this in 3 dimensions. By the way, these exponents, the way we did this calculation, it doesn't even depend on the fact that there is a vector magnetization or a scalar magnetization. Nothing mattered really. We just assumed M has, it's only pointing in one direction. I might as well have called that, let's say, the Z direction of the magnetization and gone through with this entire calculation, right? So it doesn't even care about whether it's Heisenberg with a vector magnetization or is it just a scalar Ising model or something. It's completely universal. So now you say, well, I can try and look at sort of experiments on numerics in 3D, and let me just write down sort of the answers in 3 dimensions. And let's do this for the case of the Ising example. Okay. So it turns out that the Ising model critical point, like we saw yesterday, is also closely related to the gas liquid critical point. Okay. So you can either look at this from looking at magnetic systems or fluid systems and try and extract some of these numbers. Okay. So it turns out that this beta here, let me just write out the values. This number is approximately 0.3. Okay. This number, which was 1, is approximately 1.2. This one, delta, is not 3, but rather something like 4.8. And of course, this is known to better precision than what I'm writing here. Nu equal to half, this is like 0.6, roughly 0.6. And this alpha is a slightly negative number. Sorry, is it point? Yeah, alpha here is 0.1. Okay. So although, as we saw in the van der Waals fluid example, universality was correct in the sense that a whole bunch of these fluids, when you plotted their phase diagrams or what these critical densities and what these densities were when you underwent separation into a gas and a liquid phase, they all fell on the same curve. But if you remember, that curve was not the curve given by the van der Waals theory. Okay, so this, the slides will be posted, but if you at least remember the picture. Similarly here, the various fluids and sort of magnetic systems, numerics experiment, all kind of agree on this behavior. So it looks universal, but it doesn't agree with sort of what we did from just dimensional analysis, right? So clearly something goes wrong with stuff that we have done. and quite badly wrong, because you'd have thought dimensional analysis should be extremely robust. So what went wrong? And there's at least three things that one can kind of point to, right? One is, one might be kind of a very general lesson to probably that's applicable to a number of other, problems, in most of science, which is that, in general, if I have a complicated nonlinear problem, maybe I shouldn't kind of do naive dimensional analysis in general, right? So this is some nonlinear system. Right? And maybe that's an issue, which anytime I have a nonlinear problem, maybe I have to be more careful than doing some simple dimensional analysis, because it's possible that some terms which I thought are not important somehow became important. And so while I was always comparing two terms at a time to read off these dimensions, maybe in fact, I should be more careful in kind of doing this, right? So that's one possibility, that, this is a nonlinear problem. And in fact, maybe it's true across all systems, right? Any nonlinear system, maybe I have to worry about this, like, turbulence, anything that involves nonlinear, I mean, that's out of equilibrium, but, any problem, I might have to worry about this issue, right? The second one, we can try and ask, well, what did we made this assumption, and already, people were questioning this yesterday, how good is it to assume that the magnetization is constant in space, or doesn't vary a lot? And here we've kind of taken only one place where we actually calculated something that was spatially varying. So we found that there's this one length scale, right? But other than that, we didn't take into account fluctuations, okay? And you can ask, well, can I at least estimate how important these fluctuations are, okay? And so one way to do this estimate is to say, well, what I should do is, let's assume that I am in the ordered phase, but close to the phase transition. And let's say this is my position, and let's say I'm going along one direction in some d-dimensional problem. So let's say I call this R, but R is just some slice along a line through my three-dimensional space. And I say, well, what I have is a magnetization that's uniform, M naught, right? And you could ask, well, are fluctuations important? And you might ask, well, what kind of fluctuation should I worry about when I think about this problem? So is there a idea what kind of fluctuation should I worry about? If I'm, let's say, close to a critical point, and I want to ask, well, the magnetization is not uniform, it's going to fluctuate a little bit. What would be the type of fluctuation? Anyone, just speak up, and you can just tell me and I can draw it. Slowly varying, right? So what you would expect is something is slowly varying. And the reason it's going to be slowly varying is, we already said that, oh, there is a length scale over which spins are correlated, right? And so I don't want to take one point and drop it down, because naturally the spins will kind of want to follow along. Any little deformation I make, the spins are going to follow along. So what you'd expect is that, I want to make some fluctuations around this, which will have a typical length scale of the order of the correlation length, right? And one possible thing is, you say, well, maybe it can go down or it could go up. So I could either suppress the magnetization or enhance the magnetization, which corresponds to taking that minimum that we have, this double well minimum, instead of sitting at the center of this, new minimum, I kind of go a little bit one side or the other, right? So I take this double well minimum, and instead of being exactly there, I can say, well, my fluctuation could take me here or in that direction. Is that fine? Okay, so let's assume that there's a fluctuation that kind of takes me down, and it takes me down, let's say, to 0, because this is the one I'm worried about, where I think, oh, imagine I could fluctuate just a tiny bit. I would say that's not what I'm worried about, because then say more or less I'll get the same answer. But if I could fluctuate large enough to actually be able to get here, they'll say, oh, you thought it was non-zero, but actually it's 0, the magnetization. So that's a big problem. So you'd say, well, what I want to do is to calculate, if I have droplets of the size of psi at a temperature t, and in this case, I'm going to assume t is less than 0 because I'm assuming I'm in the ordered phase. Okay, but psi in this case goes as mod t to the minus half. We didn't work it out in the ordered phase, but it's symmetric. This exponent doesn't care about whether you're below or above, and that needs separate work. But here it goes as mod t. So imagine t is less than 0. This will still scale the same way as what we wrote down here. Okay. And now what do I want to compare this with? I want to ask, imagine I could take this droplet, right? It clearly does not have, I'm not sitting at the free energy minimum anymore, right? But you might say, well, but there are thermal fluctuations, right? So if I'm at a temperature of order kBT, right, I would expect that there will be fluctuations in the energy which are of that order, right? And so what you want to ask is that, you want to ask whether can I get fluctuations and can I calculate the change in free energy and crudely equate it to the temperature, to kBT, just to get a sense of whether these fluctuations are important or not. Okay. And so let's do that. So you'd say, well, what is my, how much free energy do I lose by creating this droplet, right? Is crudely the change in free energy, right, is going to be the volume of this droplet. So in d dimensions, it's some psi to the d. That's the volume of this droplet. Sorry, change in free energy. I'm not comparing free energy per site. I'm comparing free energy change for this particular droplet to appear, right? It'll be the volume times the free energy per unit volume difference between the ordered state and the not ordered state. Okay, that we have not calculated, but it's easy to compute. So remember that the free energy is given by, we had this expression, and let me assume that, t is negative here, right? But so let me write it as minus mod t. Okay, plus, actually, let me write it as t, and we'll kind of fix it later. Okay. So let's write it as t by 2 m square plus u m4. This was my, free energy per site, right? F. Okay. And in equilibrium, this was the value of the free energy where m naught was obtained by computing the equilibrium number, right? So remember m naught, what was m naught? M naught was obtained by taking a derivative of the original f with respect to m and setting that derivative to 0, right? And so this one we obtained as some square root of negative t divided by 4u. And now I should take this and plug it back in here and figure out what the equilibrium free energy is. Right? So what is the equilibrium free energy? Let me call it F naught. Okay. What is F naught? F naught is then given by T by 2 times this thing, m naught square. So it's T by 2 times minus T over 4u coming from the first term. And then from the second term, I'll have u times m naught to the 4th power. So I should square this. So I'll get T over, sorry, did I do this right? No. Oh, sorry, m naught to the 4th power. So I should, square this and then square it again, right? So I'll get T over 4u whole square. Yeah, question? Correct. So this is a very crude. So I'm assuming that this droplet is large enough that I'm not worrying about this, but all those terms are kind of comparable. That's why, it's only by doing that full minimization are we getting this kind of size for the droplet, right? But so here I'm going to assume that, what has happened is that I'm kind of replacing it by this and ignoring the boundary terms here. Okay. You can do a more careful calculation, and we'll do that, in a bit. We'll kind of do this calculation in a bit, and we'll see that, you'll get more or less the same answer. We'll do this in 1D where you can actually work out, what the shape of this thing should be. Okay. So you kind of work out this droplet. Sorry, we were in the middle of this free energy calculation. So this thing here goes like, minus t square by 8u, and then plus t square by 16u, right? So this gives us a number that's minus t squared divided by 16. Okay. And so then you see that, okay, so what I should do is I should take this volume and multiply it by this amount. Right? This was the lowering of the free energy. So in the beginning, I had something that looked like this, but now my energy minimum looks like this. So my free energy went down from here to here. The energy went down by this much, right? That's the decrease. But now if I want to make this fluctuation, I have to pay this penalty to do that, right? So I have to take this and multiply it by t squared divided by 16. Right? And I have to demand that this number be of order kBTC. And mostly I'll omit this Boltzmann factor kb and just work in units where kb is 1. But for now, it's of that order roughly. Right? And so now you see, well, this means that this, whether or not this is important, right, depends on whether this number is much bigger than kBT or much less than kBT. Right? So I have to ask, is this much, much bigger or is it much, much less than kBT? Is this fine? Okay. And so you see, well, okay, what does this scale like? This answer actually depends on the distance to the critical point, right? So this number, remember, goes like mod t to the power of minus nu, this length scale. So this quantity goes like mod t to the minus d nu. And nu is a half in mean field theory, right? So really this thing goes like d by 2. That's this number here. This number goes like mod t squared. This number here. Okay. So now you see that this answer, right? This goes like the left-hand side goes like mod t to the power of 2 minus d by 2. Okay. And now the question whether this is much, much bigger than t or much, much less than t, right, depends on this number. Okay. So imagine this coefficient here was positive. Sorry, this exponent, imagine this exponent was positive, right? Then, oh, sorry, did I get this wrong? No, that's fine. Yeah. Okay. So imagine this coefficient is, sorry, this not coefficient, this exponent is positive. Then we'll conclude that this number is extremely small because t is very small, little t is very small. So little t raised to some positive power here is going to be an extremely small number. Okay. And if it's extremely small, then this number, the temperature will be able to overcome that small number. So you will be able to do this fluctuation because you have enough energy from the thermal bath in order to upset this uniform order, right? If on the other hand, this exponent here is negative, then when you get very close to the phase transition point, this is going to be extremely large, right? And if this is extremely large, then this will not be able to overturn, your temperature will not be able to overturn your magnetization that you created, okay? So if you do 2 minus d by 2, so let me do this here. So if 2 minus d by 2, if this exponent is positive, right? Then we said that mean field theory would break down because the temperature will exceed this number, right? And so this is the case, then mean field theory is not good. Okay. If on the other hand, this exponent is negative, then this means that mean field theory should work. Okay. And so from here, you see that the boundary that separates, whether or not mean field theory is a good starting point depends on dimension. In particular, this leads to an expression that if this is positive, then the dimension is less than 4. And if this is negative, then the dimension is bigger than 4, right? And so you see that there is, if you ask when does mean field theory work, and this is something that one of you asked yesterday, one naive expectation is that I used my central limit theorem to do simple-minded mean field theory on the lattice, where I said the effect of all the spins on the neighboring sides could be subsumed into kind of one number, which is this mean field, right? And strictly speaking, if you're using central limit theorem, you would have said maybe I should go to infinite dimensions for this to be valid, right? But there we were talking about validity of the mean field theory independent of what temperature I'm at or what I'm where I am, right? So if I want the exact results for the phase diagram at all temperatures and all fields and so on, then I really want to be sitting in this d equal to infinity kind of regime, right? But if I am asking qualitative questions about whether it's reasonable to assume uniform magnetization or not, close to the critical point, right? Then we have a somewhat more strict condition where this is not, or maybe it's not a strict condition, where if I'm at any dimension bigger than 4, I'm actually doing okay with respect to my analysis. And in dimensions less than 4, I should worry that there's a problem. Right? And these are in 3 dimensions. And so you would expect that, okay, I might have expected based on this now, that because I'm in 3D, in fact, I'm seeing some deviation. So maybe I should be worrying about these fluctuations. It's a nonlinear problem, plus I have fluctuations. Yeah? Okay. Yeah.
You say the Landau theory is still able to capture if I now include spatial variations in MR, or would we say Landau is also very
Right. So now I have to ask, well, Landau theory, at least qualitatively, we know that mean field theory doesn't work, but that doesn't mean the exponents are incorrect. Okay. So that's, I guess that's what you're asking. Or is that the question? Or?
Yeah, so then,
Correct.
now if I sort of allow spatial variations, you still get the same exponents.
Correct. So we'll have to do that a little more carefully. So we didn't do that, which is we calculated the action assuming m is constant. What if I allow for small fluctuations in m and just redo this entire calculation, saying that I'm going to keep leading order fluctuations, which people call sort of Gaussian fluctuations, and I can ask whether that is valid. And yeah, we didn't do that calculation, but it doesn't work. Sorry, I should have mentioned that. That's a good point. Okay. So leading order Gaussian fluctuations do not capture. Sorry. Okay, so how do I think about linear stability here? Right?
That's where I start, right?
Correct. Right.
So now if I take m equal to constant and just say m0 plus constant, then write down for a constant. Right. So now, so basically see that to the linear order of the solution, there is a solution.
Right. So we will encounter sort of additional divergences already at that order. Yeah. Correct. Right. So when you calculate the free energy, keeping those leading order corrections, it will turn out that the answers are more divergent or more singular than what we calculated from mean field theory. Well, okay. So to linear perturbations, you might say, well, one thing that could happen, which is why this is not necessarily a given, right? One thing that could happen is, you include these fluctuations, and all that happens is that your transition temperature, instead of being T naught, became a little smaller, right? You might say, well, you thought the critical point was somewhere because you thought it was happening when this double minimum first developed. But it's possible that, maybe that's wrong. Maybe this double minimum has to be a little deeper before your answers make sense. And so maybe all that these fluctuations capture is a shift of the location of this critical point. I guess maybe that's also what Shogun is pointing. So that's correct, which is that, in fact, we have to do more than this. We've not worked out what the fluctuations do. We will do that, right? But the point is that the fluctuations will lead to more divergent or more singular corrections to the free energy or to all these quantities than what mean field theory does. Yeah, thanks. Yeah. Mhm.
Same as saying that in reduced temperature is basically much higher. What the analysis that we done does not do anything.
Which analysis? This analysis?
To do this, we assume that the T is the reduced temperature is small, and hence when D is greater than 4,
Correct.
we see that it explodes.
Correct. Correct.
But if we are basically saying that we are shifting the reduced temperature, and this doesn't hold any.
Correct. So we'll so this gives us a hint. So this was a crude calculation, right? So what I was saying is, first of all, I didn't take into account these gradients as, was pointed out. I kind of did a naive estimation, and, all that maybe these fluctuations would have done was shifted TC, but nothing else would have changed. But all we are getting from here is, is mean field theory good or not, right? And we are saying that fluctuations will change the answer, right? Now, the change here could be, is it in the nature that it's more singular such that in fact these exponents change? Or is it like, some very weak thing that just shifts this critical point? And that we actually have not calculated anything. This was like a crude estimate of when you expect things to definitely go wrong in some sense, right? Okay. Yeah. Any other questions? Okay. So is it okay if I erase this? I'm just going to write here. So let's do one more calculation to see why things can go wrong in low dimension. And in that case, let's try and do this calculation by saying, well, I assumed that I have a certain solution where M is uniform, and I calculated the contribution of that kind of solution to my free energy, right? But I could also ask, exactly this question, but let's do this in one dimension where I can ask, are there non-uniform solutions which I should be taken into account if I wanted to sort of include corrections to my mean field theory, right? So now you ask, well, what are the kind of non-uniform solutions? And the non-uniform solutions are kind of the sort that we wrote down, that we drew, right? But let's try and take into account kind of the simplest example of a non-uniform solution where, so here I had a droplet which kind of did something like this, right? So there were two places where I had some gradients and I went from one side to the other, right? But in one dimension, I could say, well, I have other kinds of solutions which are probably less expensive, where I only have gradients on one side, okay, where I could write down solutions that simply look like this. Okay, where this is 0. Okay. This is M naught, and that is minus M. And this is going to be specific to 1D. Okay. Because you'd say, well, here the magnet looks ordered. There the magnet looks ordered, right? So both of these, remember, there are two solutions which minimize my free energy plus or minus M naught. And what we are drawing is a solution that kind of starts off near one point here. And then as a function of position, it kind of meanders over and gets stuck. Right? So it goes from plus M naught to minus M naught over some length scale. Okay. And you might say, well, that looks like it has, this must be even less energy than that one because it only involves gradients on one side and not on both the sides. Yeah. So these are, solutions are what are called soliton solutions. And this is an example of like a one soliton in this particular case, or a kink. And we can try and write down sort of, solutions to this Landau functional by doing this functional derivative at zero magnetic field. We can try and ask, in 1D, do I have sort of somehow exact solutions to that Landau free energy? In other words, I want to try and write down exact solutions to this equation where I have second derivative with respect to m of x. Sorry, let me remind myself what this thing was. So we had a t by 2 m square plus u m4 plus some kappa over 2 grad m or dx dm dx square. That was the form of the Landau free energy, right? And now we want to kind of take, and of course, integrate it over space. And now if we take derivatives, we end up with, a kappa times the second derivative of m with respect to x. To what? So this is, so this, let me just do this. Yeah, so it's some Tm right. So this gives me Tm plus some, 4um cube minus kappa d2m dx square. And I want to set that to 0. So I'm trying to solve this differential equation where kappa m square is some Tm plus cube, and T is negative. T is less than 0. So it turns out that this actually has a, sorry, this is all m of x. It turns out that there is an exact solution to this equation. Okay, so let me write it out. And then you can check that this works. So I'm not going to work out, derive this. So it turns out that there is an exact solution where this m is m naught, which is the equilibrium value of the magnetization that you would have got, multiplied by a tan hyperbolic function of x minus x naught divided by this length scale psi, which we obtained from looking at correlation. Okay, so this length scale over which this magnetization turns, okay, is the length scale that we inferred from looking at, what happens if you put in a magnetic field at one point, the magnetization has to recover. So there's certain healing length, and that healing length is what appears as the size of this soliton in this case. And this is a soliton in the sense, if I actually look at how much excess energy is there in the state, the excess energy is only localized to this region. So it's like a little particle that's sitting there where the position at the position of this kink, and so that carries sort of this localized energy in that region of space. Sorry. Correct. So this is a one soliton solution, which turns out to be exact, right? Now you can ask, well, why should I look at this solution? This assumes that the boundary condition is, I've assumed here that there's nothing out to infinity, but imagine I had periodic boundary conditions. So I say, oh, well, this thing is on a ring where the left and right have to eventually meet up, right? Then of course I can't write down solutions of the sort. At the minimum, I would have to have solutions that look like this, which is I have to have a kink followed by an anti-kink, and then eventually they have to meet up when I have periodic boundary conditions. Okay, but in general, those two kink, actually, I don't know if there are exact solutions in this for this equation for multiple kinks. But if these kinks and anti-kinks are sufficiently far apart, right, then we see that in fact the energy is extremely localized within this length scale. So long as your kink and anti-kink are kind of well separated compared to this length scale, you can more or less write down solutions for having, multiple kinks and anti-kinks. Of course, one kink has to be followed by an anti-kink in that kind of setting, right? So you go down, then you have to go back up. So it's constrained. You can't just keep going down. Yeah. Good. So now you say, okay, if this is the case, then maybe I should take into account these when I calculate my partition function, not just constant m, but in addition to constant m, these are kind of distinct solutions, and I should add up all of those solutions in order to get the net partition function, right? So let's take the one kink solution and see what we get. So the one kink solution, you would say, well, I should be calculating my cost from here, right? And my partition function for the one kink of this one soliton. So I should take into account all possible magnetization, fluctuations. So there are like different sectors now. So there's a 0 kink sector where we calculated this. Now you say, oh, there is a one kink sector, right? And so what is the contribution coming from the one kink sector? So this is like an excited state of my system in some sense, more excited than the ground state or the equilibrium minimum that we wrote down. So you'd say, oh, well, I should take into account these. And now you say, well, what is my contribution? You say I should integrate over something, right? And when we did the equilibrium, we didn't integrate over anything. We just fixed m to one value. There was nothing to integrate over. It was just stuck there. We just wrote down the free energy directly, right? Or the partition function, but that was just e to the minus beta f, or this e to the minus s that we calculated already, right? But now you say, well, I want to look at the one kink. So you say, oh, I should integrate over the configurations that I get. And now you ask, well, what are the configurations? And you say, well, I have this solution, okay? But in fact, when you solve this problem, you find that x naught is something that the energy does not care about. So x naught was a free parameter. And in fact, it just defines the place where this magnetization goes from being positive to negative, right? But if I move this soliton, and by move, I don't mean dynamically, I just take another configuration where the soliton is displaced from here to there, the energy is exactly the same, okay? That's just saying, oh, well, there is translational symmetry. If I take all the m's and translate them, I don't get any energy cost, right? And in this particular case, if I had uniform m and I translated, there's no meaning to that translation. It's a physically not distinct configuration, right? But here, if I translate it, it's actually a physically distinct configuration. So I should keep it into account. I should take that into account when I do the integral overall configuration, right? So I would have something like saying, oh, I should have some integral. And now we are kind of integrating over, we had to integrate over the magnetization, but we're saying the magnetization is, is described by this one collective coordinate, which is the position of this soliton. I don't have to worry about the precise profile is already fixed. Okay, so there's only one number that I have to integrate over, and now I have to calculate sort of what is this, contribution to the action because of this one soliton. Okay, or what is the excess free energy because of this one. Okay, and we already have, some estimate of what that is. So let me write down the answer. But we kind of did this when we did the fluctuation correction. Right, so it was some. So I'm just going to write down this answer here. So it is some mod t to the 3/2 times. Okay, these are some detailed numbers, but you don't have to worry about them. Kappa to the 1/2 divided by. So there is some excess cost that depends on the distance to the critical point. This over x naught. So I'm just saying that I should integrate over all possible configurations of the magnetization to calculate the free energy. Sorry, to calculate the partition function, right? So remember that the partition function really was z was some integral over dm, e to the minus s. Right? Now we're saying, oh, there are different types of m's, and each of them contribute to my partition function. Okay. So one that we did before in mean field theory was just a uniform m, where there was nothing that we were varying. It was just a constant. So I could just stick in that mean field m naught here, and that was the contribution. E to the minus f naught was the contribution to the partition function, right? But now we're saying, oh, but I have to take into account other types of configurations, right? And one type of configuration is this one here. Okay, but this configuration is not it's not one configuration. There are many, many configurations of this sort, which are just related by the displacement of this entire pattern, right? And all those configurations have to be included, right? But I'm not I can parameterize this entire magnetization profile for each of them by just one number, which is the position of where this kink is present, right? So that's this integral, extra integral that I have. Okay. Correct. So this was what I had calculated, except it's only one side now. So I've just repeated the calculation, but it's more or less the same up to this factor of 2. And it's taking into account these gradient terms more carefully. Because now you know the exact profile, right? You take this profile, you stick it into that integral, and you just do the integral. Yeah, so it's some integral of tan hyperbolics and so on that you have to do, but that can be worked out. Okay, so this is what the answer looks like. Okay, and so then you see that, oh, this looks like this x naught doesn't actually appear in the energy cost anywhere, or this action. So I can really pull it out. Okay. And so what you get is an answer that, let me call this some delta f or delta s, and let's call it delta s1 kink. Okay, which is just, forget this, it is this piece here. And then the other thing is you'd say, oh, this thing diverges, right? But let's assume I'm on some finite system of length L, okay, which is large, but where I have open boundary conditions so that I don't have to worry about periodic. Otherwise, I have to have kink and anti-kink. Let's assume it's like open boundary conditions. So some open chain, and 1/2 is at plus m naught, 1/2 is at minus m naught, right? Then you say, oh, well, this thing is, this integral is going to give me something proportional to L, where L is the length of my system. Okay. So this you would say, oh, this looks like, e to the minus delta s, 1 kink. And now I can try and put this L, I can bring it in the exponent here and rewrite it as minus beta times, T times L. Right, beta T is 1, sorry, log. So beta times T is just 1. Okay, delta S, let me call it beta times the free energy corresponding to this 1 kink. Right. So if I'm looking at the 1 kink solution, the answer looks like this. Right. And so you see that if I look at the total free energy, so let me call this as my e to the minus f1 kink, f total 1 kink. Right. That's my total free energy contribution coming from this thing. Then see that, oh, this goes like this energy cost, which I have. Right. Let me call this f1 kink. This is not the full free energy. Right, the total free energy is obtained by taking the log of this, the contribution. And there is this minus T times log L. Okay. And so you find that the free energy of the kink actually is much, much lower, because although this number is, it's some localized defect, it costs some energy or some free energy here, right? but it's multiplied by something, sorry, I have an additive correction here, which actually grows with the length of my system. Okay, and so I expect, in fact, that the one kink state has lower free energy than the zero kink solution. Is that fine? Okay. And so but this form is very suggestive, right? Because we know that, oh, how can I think about this? This really, we called it free energy, but really it came from some bending of some order parameter. I should really think of it like the energy. And this quantity here in a free energy, this really looks like some entropy, right? It's T times the log of number of states, and the number of states in this case is just the positions where this kink could have been. So this really looks like, it's just an energy entropy sort of competition now, where the entropy always wins. Okay. And this we could have, in some sense, without doing Landau theory, we could have also done this in the lattice model, because we would have said, oh, well, I could have drawn configurations like this in my spin model in one dimension, right? And tried to ask, well, what is the contribution of such things? And clearly, that's my kink. It's like a domain wall in this magnet where the left domain is all up, right domain is all down. This is a domain wall. There's a single domain wall now, which is this kink, right? And I clearly know that, there are many, many such solutions, because a domain wall could have been, anywhere, right? And now I should be taking into account both energy and entropy. And so I would have ended up basically with the same answer. There would have been some localized energy cost to this domain wall, because that's like a defect where spins are not parallel anymore. So it costs some energy of order J in this lattice example, right? But then this entropy will tell me that, this could have been anywhere. Okay. And so you see that, okay, that means one kink solutions, you would say, are actually favored over no kink solutions. Okay. But that tells us that, in fact, this mean field theory must completely break down, because if I allow for this one kink solution, then I say, well, why don't you calculate the magnetization? You'll say, oh, it's zero. Because, this kink, as it, I can take into account all these kink states, right? There are precisely, half of it as m equal to up, half of it as m equal to down. So the net magnetization is zero, right? Or if I want to calculate correlations, I'll say, oh, well, if I calculate short distance correlations, it looks like they are parallel. But once I kind of go past here, I would say, oh, it becomes negative. And now, of course, if one kink is, easy to make, why not make 2, 3, 4, right? So long as they are far enough apart, you can have these multi-kink solutions, which will all have, similar energy costs, just scaling up by the number of kinks, but you'll get kind of lowering of entropy, right? So you might expect, in fact, that having a lot of these kinks. So in fact, your answer at low temperature should look like a gas of kinks and anti-kinks at low temperature, which will destroy the magnetization completely, right? And in fact, it's worse, because now you say, oh, well, this destroys the magnetization at any temperature, right? So it's not just saying, oh, my critical point got shifted, the order is completely destroyed. Okay, so we see that there are these, dramatic differences and maybe not so dramatic differences between, mean field like expectations and what is the reality, right? So the reality is that you do have in 3 dimensions and even in 2 dimensions for these Ising-like systems, there is a phase transition. So that you say is kind of consistent with mean field theory. But in 1D, the transition is wiped out. Okay. But even in 3 dimensions, we are still left with this problem that, transition exists, but certain things that I expect based on, dimensional analysis to be kind of robust is actually not robust. Okay. So what we'll do, next time, which is on Friday, is, I want to do 2 things. One is we will use the 1D model as a toy example to try and start thinking about, this notion of renormalization of what it means, right? And then we'll apply it to both sort of 1D and 2D, but it'll be a very crude, way of doing the calculation. And then we'll kind of set up like a slightly more refined way of doing the same calculation, which will be useful. Yeah, so that's the plan for Friday. Yeah, cool. Yeah, okay. So it is true because, once we have this picture, I mean, we did it in Landau theory, but once we have this picture, you could ask, well, how does this generalize to 2 dimensions, right? So you could say, well, I can even make domains in 2D, right? But in 2D, I can make domains where I take this uniform thing and I make a droplet, which has, finite extent in both directions. So that is like a domain wall, which now has some length, and that's going to be my cost, right? The cost is going to depend on the length of the domain wall. And then you might say, oh, well, but there's also an entropy because, of course, I can place this in many different places. So I still get this log, right? But it actually doesn't do much because if it's a small droplet, it's not actually going to help with destroying the magnetization. But the magnetization is present over the entire area, and I'm creating little droplets, which you might say, oh, by entropic reasons, they should be there, right? So now you say, oh, well, what if I make a huge number of these droplets? Because one droplet is not enough. I want to make a large number of these droplets. And now you have to do a slightly more careful calculation of, oh, it costs so much energy. And if I take this droplet now, it's going to hit something else. So I have to do a more careful calculation of what the entropy is, because now if I have multiple droplets, I can't just freely integrate them over space, right? I can't freely move them around. They'll hit other domains. So you have to do a more careful calculation of what this competition is. Okay. So the transition survives in 2 dimensions. But if you want to think about doing it this way, then it's a more complicated calculation. Right? The other possibility is you say, what about extended domain walls? So imagine I take this in the X direction, but in the Y direction, it's uniform. So that's like a flat domain wall. And that is very good at destroying, because if I just sweep this domain wall through my system, magnetization is 0, exactly like here. But there, the problem is that this energy cost is going to be linear in L, right? And the entropy is only logarithmic, right? So the extended domain walls will not win, right? It's these little droplets. And then we know from StatMech that if you have some Ising-like model in 2 dimensions and you start heating it, you can, of course, have little droplets that flip. So this is real, that you do get little droplets of domains, but they don't destroy the magnetization till you get to some transition. Finite temperature, critical point. Yeah. Yeah. Yeah, then this won't hold, right? What we did here was assuming short range interactions and so on. So long range models in 1D in principle could have long range order. Yeah. I mean, I have not written down a model of that sort, but you could imagine that. So let's assume that the range of the interaction is like extremely long. Let's say it's infinite range, and of course it becomes like mean field because everyone is my neighbor, right? So there, of course, we know that mean field theory would work as well. So sorry, so not just infinite dimension, which was what I mentioned, but it's also true that I have infinite range interaction. Then it's like every spin in the problem is my neighbor. And again, I can use mean field like arguments to say that mean field theory is valid. Yeah. If it's truly long range, right? Like if it's some power law, then again, you have to be kind of careful. And maybe, I don't know, maybe Chauvin knows more about this from some of these, things coupled to photonic baths and so on. You can induce, for example, if there's spin models and you couple it to certain degrees of freedom, like phonons or light or something. In principle, there are these examples where you can induce longer range interactions between spins in systems. And there, it may not be infinite long range. It might be a power law, or it might be something that's distinct from, it's neither short range nor infinite range. And there it might depend on, exactly how this power law fall off is, etc. Hmm. Yeah. No, not bath. No. I'm not considering spins coupled to a, bath. I mean, of course, I'm doing equilibrium StatMech, so there is some thermal bath in my mind, right? But we don't include the bath when we're looking at the free energy of a given system, right? So this part comes from just other stuff, right? So you could have lots of contributions. So if you take a real solid, it has, interactions between electrons. Electrons can couple to phonons, right? There's lots of other stuff than the magnetization, right? So all of it can contribute to S naught. Yeah. Yeah. On the no, you have to calculate the energy, to calculate this thing. It's everything. So it costs energy, this costs energy, but so does deviating from the equilibrium mass. So all of it costs energy, right? And so presumably the dominant, I mean, there is one part coming from the fact that I have a gradient, but also in the gradient, my magnetization is deviating from the equilibrium uniform value. So all of it contributes. Yeah. Well, it depends. So if I have a line in 2 dimensions, then F kink will scale like L. Yeah, L versus log L. So L will win over log L. So extended defects are not allowed. Yep. All right.